Cool. So today's topic is alcohols. Um, this is just the index of topics that we're going to cover, and you'll see that here at the end I say that the last two topics are in the next PDF. So the first three topics, these ones over here, we'll cover today. But I just want to quickly show you something else just before I share this. I want to show you the syllabus quickly. So if you look at the syllabus, the first 3 points in the syllabus, if you look over here, these 6 points are exactly copy and paste. I literally copied and pasted it from the PDF into my notes. So these headings in my notes come directly from the syllabus. So they're reactions of ethanol. Some of them are technically not functional group conversions, but they're kind of reactions of of alcohol compounds. So anything that has an alcohol functional group. Also, it is directly in the syllabus, and it's just basically the reactivity of these things. Okay, so combustion, strictly speaking, it's not a functional group conversion because really all we're doing is forming carbon dioxide and water. So if you want to think of it as a functional group conversion, you can think of it as bond breaking and bond forming. And yes, you are forming double bonds with the C double bond O. And you are forming the new water bonds, which technically you could think of as new alcohol groups or something like that. But strictly speaking, it's not a functional group conversion. And then exactly the same as with any combustion reaction, if there's oxygen involved, you're going to get carbon dioxide and you're going to get water. So no other byproducts in that case. It's basically just it's really just saying, can you put something with alcohol? Can you put something with alcohol, form the products and balance the chemical equation? So that's probably as difficult as it's going to get, is figuring out how to balance your chemical equation. Also by identifying the number of carbons, etc., counting it up, and then obviously writing some sort of molecular formula if you wanted to. So this would be C4H H10O. And then when that combusts, you get all of the products over there. Cool. C5H12O. But that's not important. You can go and figure that out. But in reality, anything that contains carbon, hydrogen, and oxygen, you'll see later ketones, aldehydes, carboxylic acids, anything that has carbon, hydrogen, and oxygen can technically be combusted. So you can literally combust any organic compound and it's going to give you carbon dioxide and water. But combustion of ethanol is particularly useful because we use it as a fuel. So some cars these days drive off ethanol. Cool. So nothing too interesting about combustion. Just remember it's always involved oxygen and the products are always carbon dioxide and water. Cool. So this is a slightly more interesting one. You can take an alcohol and you can convert it to a halogen or alkane. So I know what you're probably thinking. What we literally did yesterday or the day before is we did the backwards reaction. So what we did previously is we did that. So now we're not doing that one. What we're doing now is the forward one, and that's taking the alcohol and turning it into the halogen or alkane. Cool. So it's almost identical. It's the same sort of process. It's also a substitution reaction, except this time we're taking off the alcohol and we're putting on the halogen. Now the interesting thing with this reaction is that we don't add the halogen directly. So you'll see here in the general conversion, I put the halogen over there where the yellow is. So if you look at that, you're adding the halogen. But in reality, the halogen comes from a combination of the halogen salt plus sulfuric acid. So to form the HCl, I actually have to react sodium chloride with concentrated sulfuric acid, and that's going to produce the HCl. And then similarly, if I wanted HBr, I can react KBr and H2SO4. So the most important thing here is that you're going to add concentrated sulfuric acid and then some sort of halide salt. And you'll see here that I tell you it can be a sodium salt or a potassium salt. So quickly, if you have a pen and paper, just quickly write this down. If I say to you, I have potassium, hang on, I want the smaller pen. If I give you potassium iodide plus concentrated H2SO4, forget about this NaHSO4, that's not important. The question is which hydrogen halide would you form in that case? So just quickly think about it and give a thumbs up when you're done. Also, if I give you potassium iodide and if I react it with concentrated sulfuric acid, which hydrogen halide will I form? Glucose is good. Cool, Stefan's good. And I think everyone's good. Okay, cool. So Stefan, what's the hydrogen halide formed?
Hydrogen iodine.
Correct. So HI. So it's as simple as that. All you're really doing is you're identifying the fact that there's iodine here, and then you're reacting it with the concentrated H2SO4. So I just want to show you quickly. This will be on the YouTube for the guys to see at home or whoever's on there. If I took away the potassium over there and if I put sodium in front, so if I just swap that and I made sodium, would you agree with me that I would get the same product? Yeah, it's the same product, correct? Because all I'm interested in is the fact that I'm bringing the iodine to the party. So if I bring the iodine to the party in some sort of salt form, either sodium salt or potassium salt, I just need to react it with sulfuric acid and I'll form the hydrogen halide. So if you look in the textbook, they call this in situ. I'll just write it here. It's in the textbook. If you read, it says in situ preparation. So we actually prepare the hydrogen halide in the chemical reaction itself. But it's very important that we don't first prepare the hydrogen halide and then put the chemical in. We literally just chuck everything in together. So if in this example here, the ethanol is mixed directly with the mixture of sodium bromide and sulfuric acid. And if you remember, those two are going to combine. I want the bromine from there. I want the hydrogen from there, and those two are going to form the HBr. Sorry, the yellow is a bit dull. I can't see that. Let's use red. That's the HBr, and that's the HBr that's going to react over there. Cool. So we don't first make that mixture and then let it sit for a little bit. We literally just lump everything together in the beaker and warm it up together. And then they give this term here under reflux. So it's intense heat for a long period of time. Well, and then all you'll notice here is that the OH group here, that OH group has been replaced by the bromine group. Also, instead of having an alcohol, now we have a halogen alkane. So ethanol gets converted to bromoethane. Cool. Any questions so far?
No.
You're good? Happy days? Good, good, good. So we can look at another example here, examples of unfamiliar molecules. Remember when I say unfamiliar, I just mean, yes, Angelica?
Sorry,
Yeah,
I
talk to me.
just wanted to ask, when simplified by ethanol, is it only ethanol we should know, or should we know other
All of
molecules
them,
as well?
So very good question. Very excellent question. The syllabus uses that word exemplified a lot. So it says here, exemplified. And all exemplified mean is using ethanol as an example. You can apply this to everything else, but ethanol is a good example to start with. So you'll notice that all the notes, if you've been paying attention, I almost always start with ethanol, or I always start with the smallest alkane, which would be like ethene or ethane or whatever, because they always say exemplified by the smallest possible one, and then they often say something like propane or propene. So as an example, using propane or propene. So you'll see that I always start with the smallest examples, but then you have to be able to apply this knowledge to any unfamiliar situation. Also, very good question. Thank you for that. Also, as an example, use ethanol and then apply the knowledge to any other molecule. Cool, so here's unfamiliar molecules. This one at the top is not too unfamiliar. You could probably name that when we get to that. It's just a straight chain alkane with a branch. And then you'll see that the only thing we've done to it is converted the alcohol, the OH group, to an iodine over there. And then I make a note of this at the bottom when you go home and read about it. The hydrogen iodide is prepared using either potassium iodide or sodium iodide. Also, it's those two, it's a combination of either of those two. And it's that goes over there and reacts over there like that. Cool. So the sulfuric acid and that other funny little byproduct, they have nothing to do with the reaction. Cool. The textbook explains it a little bit. If you go and read the page on the textbook, it does explain it. It gives a little bit of detail about that. They talk about why they make it that way. Oh, and then this last one, don't worry about the complicated mess on this side over here. That's not relevant because all you notice is that I identify my important functional group, which is the alcohol, and it can get converted to the chlorine. So I can ignore the rest of the molecule, even though it looks horrible and complicated. So that's not important over there. Cool, any questions so far? You good? Yep, so it's basically just a functional group conversion. We can turn an alcohol into a halogen. And it's just a straight one-for-one conversion. The alcohol comes off and the halogen comes off. So I just want to show you quickly in your functional group conversions, if you go to your mind map over here, this conversion is on this over here. We might have talked about it or seen it yesterday. It's alcohols to halogenoalkanes. It's this path over here, and it's distilled from a mixture of alcohol, concentrated sulfuric acid, and the potassium or the sodium salt. Cool. This warm with NaBH and Br, this over here is actually for this conversion over here. So just ignore that. That's not the conversion we're looking at. Cool. So the conversion we're looking at is this one. Distilled from a mixture of alcohol, concentrated sulfuric acid, and the potassium or the sodium salt. Cool, so that's another one ticked off our list that we're done with. Yeah, there we go. Cool, so whenever you see an OH in a molecule, you can convert it back to a halogen if you want to. And then you can go backwards and forwards if you really wanted to. You could take the halogen or alkane, and then you could do the hydrolysis, and you could go back to the alcohol. And you could do like a little backwards forward thing if you really wanted to. Cool. The next one really is not technically a functional group conversion. It's almost like an acid-base kind of thing. It's not quite an acid-base thing. It's almost a redox reaction, almost an acid base. But really what we do is we take an alcohol and we react with sodium, and what we form is a sodium ions. But what we also produce is what's called an alkoxide ion. So you'll see here that we form what's called an alkoxide. And if you break the word down, it's just saying that the first part of the word is telling you that it's some form of alkane, and then the second part of the word is sort of telling you that it's some sort of oxide. So it's an alkane that contains an oxygen, but the oxygen is not an atom, it's a ion, because we know that IDE is for ions. So it's an alkane that contains an alcohol that has been turned into an ion. Also, just to show you a couple of examples, if you look at the one of ethanol, here's the regular good old-fashioned ethanol on the left. That's the ethanol. We reacted with the sodium. And then what we form is the sodium ethoxide. That's what this is over here. But sodium ethoxide is ionic. So it's actually an ionic compound, and it's not bonded together. So if you remember from ionic bonding, if I have something that's negative and if I have something that's positive, they're technically not bonded together. They'll live together either in a solution, or if they're in solid form, they'll live together in a lattice. Also, it's a solid ionic compound. Also, this is a solid ionic compound. And if it's already in solution, if it's still dissolved in the ethanol, you'll see that we have the ethoxide ion and the sodium ion separate. Also, when we say that the sodium ethoxide is technically dissolved, if we remove the excess alcohol, we will have pure solid sodium ethoxide. Also, these are not liquids. They're actually they're solid ionic compounds. So if you remove all the excess solvent, you'll actually isolate them as solid powders. I had to think about this quite a bit yesterday. I had to do a bit of research and a bit of Googling just to remind myself how this worked. Also, just to have a couple of looks at there's reactions with simple examples. So you'll notice here that if you start with methanol, there's meth, you get the meth oxide. If you start with eth, you get the eth oxide. If you start with prop, you get the prop oxide, and you get the point. So in other words, the oxide, the name of the oxide basically sounds the same as the name of the original alcohol. The only thing is you replace the OL, which is the ANOL for the alcohol, with the oxide. And the reason is because you've taken away that hydrogen and you formed an ion. Also, it has a negative oxygen ion attached to that group. And then if you just carry on, there's one more example here. So unfamiliar molecules, things that look a bit messy. And in this case here, I've shown you both examples where you can draw them as together. So the O with the Na next to each other, or you can separate it into an O negative and an Na plus. Well, and the same with this. Here's the O negative, here's the Na plus. And in this case, I haven't even written the middle form where they join together because it's an ionic compound. Well, any questions? Anything that you need help with or assistance, or is that pretty straightforward? Yep, you good? Good. And you'll see later that this is a useful reaction because we can use this to test for the presence of an alcohol group. So if we reacted with sodium, it'll become a very basic solution. And if we use some form of indicator like phenolphthalein or universal indicator, or whatever, it's going to indicate that the solution turned very basic. And that's a good indication that an alcohol group is present. Also, you'll see that later when we do sort of testing for alcohols in the next topic. Thing. But it's also very useful because these become extremely powerful bases. So if you take away the sodium ion, if you ignore that for a second, this molecule here is an extremely powerful base. So this over here is a very strong base. Very strong base. And the reason it's a very strong base is because we broke a very stable bond. The OH bond actually didn't want to break, and we broke it apart. And this thing here is going to be looking for hydrogen ions. So as soon as it sees a molecule that has hydrogen bonds, an atom bonded to a hydrogen, it's going to want to steal that hydrogen. So let's say, for example, CH4 comes along. Ooh, so CH4 comes along. It's possible that this ion, this ethoxide ion here, could potentially steal one of these hydrogens, even though we don't technically think of methane as being an acid. The ethoxide ion might be powerful enough to actually steal one of those. So just a little bit of acid-base thing. So in this case, the methane would be the acid, and this here would be the base in terms of Bronsted-Lowry acid-base donor and acceptor. Cool. So we've created. Yeah, talk to me.
The what ion can steal the hydrogen?
The ethoxide ion, or the oxide ion. Let's just call it oxide for short, because this one I don't know what its name is, but they're all forms of oxide ion. You'll see that they all contain the word oxide in it. So if you look carefully here, it's oxide, 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 oxide. They're basically oxide ions. And the simplest example, the one that you know, is the hydroxide ion. So you know very well the hydroxide, which is just OH negative. Cool. So it's any oxygen containing molecule that has a negative charge on the oxygen, obviously.
Okay, thank you, sir.
No problem. And it's very good if you think about it in this case. OH ions are extremely good bases because they're looking for hydrogen ions to form water. Cool. So that's why sodium hydroxide would be a good base, because once the OH is in solution, the OH wants a hydrogen so that it can become neutral and become water. And it's the same with all of these ethoxide or oxide compounds. They're looking for hydrogens. Cool. I don't know why they want you to know that. It's not particularly useful in the syllabus, but you never know. They might ask you something about it in a question. We'll have a look at those later. Cool. Any questions so far? You happy? Good. Everyone's happy. Good. Then we'll move on to part 2. Cool. Now, part 2 is going to be the more interesting one. Part 2 is the actual functional group conversions. And part 2 is going to show you how we can go from alcohols to aldehydes, ketones, and carboxylic acids. So it's really going to fill in a lot of pathways on our. It's going to fill in a lot of pathways on this diagram over here. So when we look at this, we're going to fill in. We're going to do alcohol to aldehyde. We're going to do alcohol to carboxylic acid all the way. And then what's not on here, which you need to go and fill in for yourself when you make your own diagram later, is you need to add the ketones. So the ketones are not on this, but we can go from an alcohol also now to a ketone. Also, we'll come back to this diagram and we'll see what we've learned by the end of the lesson. Cool. So I urge you, please go read the textbook, page 226, 230, 231. They'll give you diagrams of what they mean by reflux and distillation. And in fact, you'll see it again later when we talk more about aldehydes and ketones. It's actually in that chapter again. They show you what the distillation and what the reflux looks like. Cool. So just to go over a primary view, this is a summary of all the types of alcohols, primary, secondary, tertiary, and then all 3 in 1. But what I did was I snipped this apart and I took it into individual little things here. Cool. So what you've got to do is you've got to look where the alcohol is. The alcohol is over here. There's the OH, and it's attached to this carbon over here. And what we're saying is that this particular carbon is only attached to one other carbon. So if you look at the bond next to it, it's only attached to that carbon over there. And this is what we call a primary alcohol. Also, it's primary if it's attached to a carbon that is only attached to one other carbon. So we're focusing on the first point of attachment, and then we're asking at that point of attachment, how many other carbons is that attached to? Also, it's a little bit confusing at first, but you'll identify it. And very often you'll find them at the end of molecules. So where the CH3 group is, it'll be somewhere around that point. So you'll most often find them towards the end of a molecule. In fact, what I'm saying is wrong. You'll always find them at the end of a molecule. Cool. So you can look at long molecules, big, ugly ones. You can look at examples, make something really ugly like that. Then you, oopsie. You can make something ugly like that, something ugly like that, and then you can put an OH here. And that's a primary alcohol over there, because if you look at this carbon, that carbon over there, that's the first point of attachment. That's similar to this one, and it's only attached by a single bond to this carbon over here, which is similar to that carbon over there. Cool, so that would be a primary alcohol. Cool, any questions? Are you happy with that? So primary alcohol is almost always at the end of a molecule where the carbon is attached to only one other carbon. Cool, then you can look at secondary alcohols. The secondary alcohol, you've got to find, there's the OH, there's the carbon that it's attached to. Then you've got to ask yourself, that yellow carbon, how many carbons is that attached to? And it's attached to 2 other carbons. So when I highlight this now, you'll see the 2 other carbons that I'm referring to are, let's do them in green. This, green. That green carbon there, that green carbon. Those are the 2 other carbons that it's attached to. Also, if you looked at a long, ugly, complicated molecule, something big like that, put an ugly group over here, put a bromine there. And if you put your OH group there, that would be a secondary alcohol. So I'll highlight it for you here. There's the yellow carbon that it's firstly attached to. And then the 2 green carbons would be, whoopsie, not yellow, green, that green one and that green one over there. So that would be a secondary alcohol. Cool, any questions? You happy with that? Yep, good. So you look at the first point of attachment, you look what the OH is connected to, and then you ask yourself, that carbon that the OH is connected to, how many other carbons is that connected to? And then you get your secondary if it's 2. Well, and then tertiary you don't find very often. Tertiary is a very bulky sort of molecule, and it's bonded to 3. So you have your carbon in the middle, and it's bonded to 3 other carbons, 1, 2, 3, and those are the 3 other carbon atoms. So you would have to find a really ugly looking molecule for this. You'd have to have something like this, where there's a carbon there, and then your OH group would be on the same carbon, OH, like that. So I'll use the same colors to show you. That's the yellow carbon. And then the 3 green carbons are that one, and that one. Cool, so that would be a tertiary carbon. And then another way that you can think about it is that a tertiary carbon, this one in the middle, will never have hydrogens. So it'll never have a hydrogen on it because it's bonded to 3 other carbons. So there's no space for extra hydrogens. Cool. And then you could also go back and apply the same logic over here. You could count the number of hydrogens and you could say, well, if that's 1 hydrogen, then it's secondary. And on primary, you'll have 2 hydrogens. So that's another way of looking at it. That's the wrong place, sorry. I meant to say those 2 hydrogens. Yeah. So there's both ways you can look at it. Count the number of hydrogens or count the number of carbons. Cool, and then you can find all 3 in one molecule. So you have to look at molecules carefully, and you have to identify whether they are primary, tertiary, or secondary. So let's look at this first one. It's attached to that carbon, and that carbon is only attached to 1 other carbon. So that would be primary. Ooh, so that's a primary alcohol. Oopsie, get rid of that. Lead. Then you can look at the second one. You can say this alcohol group here is attached to that carbon, and that carbon is attached to that carbon, and that carbon over there. Cool. So this one would be a tertiary alcohol. And then you could apply the same logic to the last one. You could just look at that and say, just give me a second, have a look at the first carbon that the OH is attached to, and that carbon is only attached to 2 other carbons. So that would be a secondary alcohol. So a large molecule with many functional groups, bromines, chlorines, hydrogens, oxygens, OHs, can have all different types of alcohols, primary, secondary, or tertiary. And if you look at examples like we did yesterday, for example, like ascorbic acid that we Googled on the internet, it probably has a mixture of primary, secondary, and tertiary.
So,
Yellow.
when we form an alcohol, do we have to or how do we, say, okay, this is going to be a primary alcohol?
Very good question. It depends where its position is. So if you were going to form it from a halogen, for example, if the halogen was on the terminal carbon, on the last carbon, it would form a primary alcohol. If it was somewhere in the middle of a molecule, you would form a secondary or a tertiary alcohol. So that's a very good question. I'll show you an example of that just now. I'll show you, you can have a look. Also, if you have a look at this one quickly, this is ascorbic acid. This is just vitamin C. If you look at this OH here, it's attached to that carbon. And that carbon is only attached to 1 other carbon. So we would consider this one here primary alcohol. Cool, and then I'll do the same one. Oh no, I have to erase it because I have to get rid of everything else. So get rid of all of that. Then you can look at the second OH group. You can look at this one. It's attached to that carbon, and that carbon is attached to this carbon and that carbon. So this one is secondary. These 2 over here are a little bit confusing because they're attached to a double bond. So we won't really talk about what they are. They can become primary, secondary, or tertiary if we add, let's say, hydrogen to that double bond and get rid of the double bond. And in that case, they would both be secondary alcohols. But at the moment, they're not primary, secondary, or tertiary. They're attached to the double bond, which is a whole different story. Cool. So we don't have a lot of time left. So what I'm going to let you do is I'm going to let you go on now. And I want you to read about mild oxidation. You'll see here there's mild oxidation to form the aldehyde. And then there's a couple of good examples there. And then there's strong oxidation to form the carboxylic acid. And we do this under reflux You'll see here that I've highlighted the words that are very important: distillation, mild, and then strong and reflux. And then when you're done with that, you'll see that your secondary alcohols get formed to ketones. So you won't form aldehydes and carboxylic acids. And it makes sense because they're somewhere in the middle of a molecule. You can't have an aldehyde or a carboxylic acid anywhere other than the end of a molecule. So you'll only get those two from primary alcohols. Cool, so go have a look and read that, and then have a look at the couple of examples there. And then just read the textbook quickly to see what they say about reflux and distillation. Cool, any questions?
So, do these primary, secondary, and tertiary structures relate to stability or something?
Yes and no, but it's also just about position. So in reality, it's actually just about the position of the functional group. So yes, in terms of the mechanism of substitution, the stability would be important. You'll see that the one does SN1 mechanism and the other one does SN2 mechanism. But as far as the position on the molecule, it's just where we put it or where we wanted it or where nature formed it. So like you asked, if I take a molecule like this, where there's a chlorine there, and if I do the reaction with H2O distillation, I'm going to get a primary alcohol because it's going to form on the last carbon. Also, sorry, that's in the highlighter pen, but I'm sure you can see that. Oh, but if I just swap the Cl, if I took the Cl off there, and if I put the Cl onto a different carbon, so if I put the Cl over there, and I did the same H2O with distillation, my OH group would form over there. And in that case, it would be a secondary alcohol. So whether you form primary or secondary or tertiary alcohols depends on what you started with. So where the position of the halogen-alkane was. And then you'll see later when we do aldehydes and ketones, we can reduce them and we can take them back into alcohols. So we're going to do the forward today, and then in a few days' time, we'll do the backwards. Cool. I'll see you guys. I'll see some of you in physics. Otherwise, I'll see the rest of you tomorrow. In fact, I'll see you all in physics. Yeah, talk to me.
Does the alcohol
Yeah.
follow the rule of wanting the carbon with the least number of hydrogens, or?
Well, in this case, it's a 1-for-1 substitution. You put it on where it came off. So it has to get put on where it came off. It doesn't have a choice.